Ever wondered how your favorite video games or virtual reality experiences craft those hyper-realistic 3D worlds? It's not magic, it's cutting-edge computer vision. Today, we're unpacking a breakthrough called PM loss, a technique reshaping how we turn 2D images into precise 3D models. Let's dive into the science behind it. Here's the core challenge. When converting 2D photos into 3D scenes, computers struggle with depth estimation. Think of it like this. If you take photos of a car from every angle, a depth map tries to map each pixel's distance from the camera. But at edges where the car meets the background, those maps often fail. They might skip pixels or produce jagged transitions, creating gaps that look like digital static. The result? 3D models that are blurry, distorted, or outright broken. Researchers tackled this by introducing point maps, a more precise approach. Unlike depth maps, which only track distance, point maps assign each pixel a full 3D coordinate x, y, z. It's like giving every pixel a spatial address, not just a height value. But here's the trade-off. Aligning these point maps with camera movements is computationally heavy, making them tough to use in real-time applications. Enter PM loss, a hybrid solution that marries the speed of depth maps with the accuracy of point maps. The method uses a pre-trained model to generate a point map as a geometric guide. This guide acts like a teacher, showing the 3D model where real-world geometry should exist. By comparing the model's predictions to this point map, PM loss actively corrects depth map errors, filling gaps and smoothing transitions. Imagine reconstructing a house from a photo. A depth map might give you a shaky sketch of the roof's height, but a point map is like a 3D ruler telling you exactly where each corner goes. PM loss uses that ruler to refine your sketch, turning a wobbly line into a crisp, accurate structure. Testing on large datasets, the team found PM loss significantly improved 3D Gaussian models, those tiny 3D dots that form surfaces. Rendered views became sharper, with fewer artifacts. Crucially, the technique works with existing models, avoiding the need for complete overhauls. Let's say you're building a 3D city for a game. You want realism, but balancing speed, quality, and simplicity is like juggling flaming torches while solving a Rubik's Cube. PM loss simplifies this by distilling a point map's essence into a streamlined training process. It's like giving the model a cheat sheet. Instead of teaching it every step, you show it the final answer and let it optimize the path. But here's the catch. The point map is the foundation. If it's blurry or incomplete, like a blueprint missing walls, those flaws propagate into the final model. Researchers even observed bizarre cases where inaccurate point maps caused 3D objects to float midair, like digital ghosts. So while PM loss is a leap forward, its success hinges on fixing those shaky blueprints first. Now, picture augmented reality glasses that overlay digital details onto the real world, or VR environments so immersive you could almost touch them. PM loss could make this faster, cheaper, and more accessible. But there's a double-edged sword. The same tools that preserve ancient ruins in digital form could also create fake historical sites or deepfake landscapes. The future of 3D tech isn't just about visual polish, it's about building responsibly. And that starts with fixing the foundations. So next time you see a virtual world that feels too perfect, remember, it's not just about the pixels. It's about the point maps behind them,